All right, here we are going to be talking about the lung. So I'm going to draw a lung real quick. So if that's the lung, touching the lung, we have a few different membranes, or a couple different membranes. So directly touching the lung is going to be a terrible drawing, but this is the visceral pleura. And then we have an outer pleura, or layer, membrane is a better word. And this is the parietal pleura. And these membranes are essential in creating negative pressure in this space to be able to pull the lung out so air can get in. So we'll dive deep into that. So this is right here to here, all over, is the intrapleural space. Or just pleural space, that works too. And in this space, there's fluid. There's probably water and other things, but there's fluid. And so it creates like a suction. And so these are actually touching. So it's not necessarily a space. We just draw out a space to kind of show that this parietal is separate from the visceral. And there's fluid in it, so technically it is a space. But it sucks tight regardless because of the fluid. And so a lung at rest is about -3 millimeters of mercury of pressure in this space. And so we inhale and exhale, obviously. Let's start with inhale. When we inhale, our sternum, ribs, intercostal muscles, sternocleidomastoid, scalenes, there's probably others, but it kind of, our sternum goes up and our ribs go out, and it pulls the parietal pleura, which is attached to these other muscles, bones, tissues, whatever, and it creates a bigger space. And because of this, the fluid and the pressure, the negative pressure in this space, this visceral pleura will go with it. And so as we start to inhale, we actually get to a -8 millimeters of mercury. And that's a pretty negative pressure, and it creates a really good vacuum. And so this visceral pleura will stick this parietal, and it will expand the whole lung, because the lung is connected to this parietal pleura as well. As we expand the whole lung, Boyle's law says if we have a high volume, then we'll have a low pressure. So when we create lots of volume in the space and the lung expands, we have also alveoli. I don't really know how to draw it. I'll just draw it like this. But the alveoli, when it expands, elastin also expands this. And in the alveoli, when we're inhaling, we're still talking about that, it becomes a -1 millimeters of mercury of pressure in the alveoli. Now gas, it goes from high to low concentrations, high to low pressure, similar to concentrations we've seen in blood vessels and cells and different things. So with this negative pressure and the outside pressure, it's 760, but we're gonna measure it as 0. Air is gonna rush into this alveoli. So as we inhale, air rushes in. When we exhale and force all the air out, at the end of exhalation, we actually have a -1 millimeter of mercury in pressure in this intrapleural space. And basically all that means is the lung wants to collapse and it's a lot smaller. And I'll change to black again. Our -1 goes to 0 and then changes eventually to +1 pressure in this alveoli. and outside is 0, and so it's going to flow from high to low pressure, and so air will leave back out as we exhale, obviously pushing the air out. So that's the membranes and pressures that we deal with in order to get our alveoli full of air, new air and oxygen to be able to oxygenate the lungs. So if we have a pneumothorax, or basically if we have a break into the parietal pressure, in the parietal membrane. So if like we crack a rib and it pokes a hole in this parietal pleura, there's a number of different things, but that's a great example. This negative pressure now becomes 0, right? It matches our 760 outside, but we'll call it 0. And so now when we inhale, or no, even at rest, basically this visceral pleura does not hang on to the parietal pleura anymore, because this negative pressure kind of created a vacuum, you could say. And so our lung is just going to collapse, because our lung naturally wants to collapse. We have elastin and different things that makes it just want to shrink. And the parietal pleura and visceral pleura connecting to each other was making it pull apart. So our lung's going to collapse, and even when we inhale, it's not going to do anything. And so it's not going to create this negative pressure in the alveoli, and we're not going to get any air in. So that's really bad. A pneumothorax, really bad. All right. Now we're going to just draw an alveoli. And in our alveoli, we have fluid in it as well, specifically H2O. And we have H2O, or water, all along here. And with hydrogen bonds, it's going to create, they're going to kind of want to hang on to each other and create what's called a surface tension in this alveoli. So the surface tension creates a problem. So we have something called Laplace's law, which is P is equal to 2T over R. And P is the pressure pushing in on the alveolus. T is tension. And R, it'll be a little r actually, not a big R. And little r's means radius. So if we have a big radius, if this increases, the pressure pushing in on this alveolus is actually going to decrease. If we have a very small radius, so if this drops, then pressure is going to increase. There's just more pressure putting on. We could also play with tension. If there's increase in tension, or whoops, that's a bad arrow. Or in this case, surface tension, because of these water molecules, there's an increase in pressure. And so you can see, if we want to expand our alveoli, this high pressure and high tension is going to keep it from, or you at least have to work really hard to expand it. And so we make something from a pneumocyte type 2 cell called surfactant. And what surfactant is, it's a substance, molecules, basically disrupts these hydrogen bonds, and so it relieves surface tension. I'll write that. Relieves, I spelled relieves wrong. I don't know how to spell relieves. How do you spell relieves? Doesn't matter. Relieves surface tension. Forgive my spelling. Tension. So, coming back to our Laplace's law, if we decrease our surface tension, then we decrease the pressure that's pushing in on the alveolus, making it easier to breathe or more compliant and less elastic. So that's surfactant. Okay, now we're going to talk about the alveolar gas equation. I'll pause it while I write it out. So the alveolar gas equation is PaO2 is equal to, should probably write it a little smaller because it's a big equation. We'll start here. Yeah, you can see that. So it's big A, because its pressure in the alveoli of oxygen is equal to FiO2 times pressure of the atmosphere minus pressure of water minus, you still see, minus PaCO2, I believe. Let me double check that real quick. Yeah, over big R. Okay, so pressure in the alveolus of oxygen is equal to the percentage of oxygen present, which is 0.20, it's 21%. Use a different color, actually. So 21% times pressure of the atmosphere, which is 760. Pressure of water, which is just 50. This is millimeters of mercury, both of these. Minus the pressure of CO2 is 40 millimeters of mercury. And R is equal to CO2 over O2 used up in the cell. I don't know how to explain it fully, but basically for this much O2 we use, this much CO2 comes back out. And so if we're talking sugars or carbohydrates in our metabolism, if we push in 6 O2, we're gonna get out 6 CO2. And so that will be equal to 1. But if we're talking about fats do it a little different. And we do more O2 than we get CO2 out. It's like, I think the actual the equation is 23 over 16. So for the 23 molecules of O2 we put in, we get 16 CO2 out. And so that is actually, the ratio is like 0.75. We also have proteins that we metabolize. R in a healthy person, we've determined is 0.85. So we use up a little more oxygen than we get out CO2. So if we do this this equation, I'm not going to do it, but it comes out to be 102. So our pressure in the alveolus of oxygen should be 102. The reason this is important clinically is because if we have a patient and we measure this PaO2 and it's not 102, it's greater than or less than something we wouldn't expect, then something is not right. And the best way, so before we can figure out what is going on, we got to give him oxygen because his tissues will start to die and he'll eventually die. So to save his life, we can increase or decrease this. And most of the time we just have to increase the oxygen. So I don't know what a percentage is, but as we increase the oxygen, if this was low, I don't know any numbers or math really, but let's say this is 90. We increase the oxygen enough to where after all these different pressures, we get this back to 102. That's so bad. So we can play with the amount of oxygen that they're intaking to get the alveolus the right amount of oxygen. Okay, a little bit about how CO2 and oxygen exchange. So we'll have CO2 basically goes out of the red blood cell and then it goes into the tissues first and then goes out to the alveolus to be pushed back out. And then our oxygen, as we inhale, we bring it into the alveolus, so 2, and then it's brought in to the tissues and brought in to the red blood cell and will attach to hemoglobin. So this hemoglobin will attach 4 different oxygen And how they transport is a pressure gradient. And so on this side, O2 will be about 104, and in the tissues about 100, and CO2 will be about 45 here and 40 up here, so it'll go from high to low pressure gradient. And that's how oxygen and CO2 go back and forth. CO2 in the tissues makes up about 7% of all the CO2. We have another 23% here in the red blood cell, and it actually attaches to hemoglobin. I'll explain a little more about that in a bit. 23%. And then most of it, 70% of it, is just in its bicarb form, HCO3. And because we have a little channel here, bicarb will come in, combine with a proton or an H that's in here, and make CO2, get on the hemoglobin. But most of it is in the plasma as HCO3. Our oxygen, most of it is attached to hemoglobin, 98%. And then about less than, but probably around 2% is in the tissues. So that's all about CO2 and oxygen exchange. I'm going to erase this. We're going to talk about a hemoglobin saturation curve and how oxygen gets on and binds and then gets kicked off as well to go to the tissues. So I'll erase that. All right, so this is what a dissociation curve looks like. And so over on the y-axis, we have a percent of saturation of the hemoglobin with oxygen, and then pressure of oxygen in the tissues. And the curve looks like this. Let's see if I can get this right. Looks something like that. So lots of pressure in the tissues, or in other words, lots of oxygen in the tissues, our saturation of hemoglobin is up at 98%, where it should be. The less oxygen we have in our tissues, the more oxygen need to be pulled out of the blood. And so we start to dip a little bit. Until we get to around 40, then we start to dip dramatically. Because once the tissues gets around 40 millimeters of mercury of pressure of oxygen, then we really need to start using the oxygen off of the hemoglobin. And so that's why this curve starts to dump off really fast. And there's factors that determine this curve as well. Because there is, I'll just draw it right here. So there's a T state and an R state of hemoglobin. And the T state, it can change its affinity, so it's less, it has a less affinity for oxygen. And R state is a higher affinity for oxygen. R state is like our normal curve. Hangs on to oxygen until it has to be pulled away. Erase that. But there's a couple factors that can influence our T state. To make it in the T state and bump off those oxygens, we can have high CO2, high H+, lots of protons, high 2,3 bisphosphate glycerate, so 2,3-BPG, and then I'll write it under, there's another one, temperature, increase in temp. To get it to the R state, so we hold on to oxygen longer, decrease temp, right? Decrease CO2, double check and see if there's any more. Yeah, there's probably more. It's probably all of these, just the opposite. But So when we have in our T state, all these occur, that shifts our curve to the right. And if we have it in our R state even more, if it's really cold, low CO2, it can actually shift our curve to the left, where it hangs on to oxygen longer, right? Even less than 40 before it starts to really dump off of the hemoglobin. So hopefully that made sense. That's the saturation curve and how factors can affect that. Last few minute details about the factors that can influence the saturation of hemoglobin. A little acronym is CADET. It's really good to memorize. CO2, acidity, let's see. Sorry. DPG, which is also the 2,3-bisphosphate glycerate. Exercise, or temperature. And so CO2, if there's lots of CO2, it'll bind. Oh, I'm gonna use a different color. It will bind, use this, and bump off an oxygen. If we have lots of CO2 as well, remember that'll create the equation. CO2 plus water can make HCO3 plus hydrogen. This hydrogen can come and bind and kick off. So the acidity can kick off an oxygen. In hypoxic situations, so when there's low O2, lots of CO2, we make this 2,3-bisphosphate glycerate, or bisphosphoglycerate, and it lowers the affinity of oxygen. So with 2,3-BPG, an oxygen will get kicked off. And then temperature as well and exercise will ensure that the oxygen is not attached to hemoglobin but out into the tissues replenishing. So that's a little more on that. And that's all for this video.